Hello everybody, our chapter 21 video today is all about comparing two proportions. Up to this point, we have done confidence intervals and hypothesis testing for one proportion. Now we're going to actually be comparing two different populations and therefore two different proportions. When it comes to comparing two proportions, this is where a lot of real world applicability comes into play. So when we compare two proportions, we often want to know, how do two different groups differ from one another? So for example, we could compare males and females, or we could compare middle schoolers and high schoolers. We just really want to know, what is the difference between two groups? We also might want to know whether a treatment is better than a placebo, or whether a new treatment is better than the old treatment, depending on what kind of drug or vaccine that you're trying to create. We also might want to compare this year's results to last year's results, or 10 years ago, just to see if there's any significant difference between now and then. So like I said, comparing two proportions really does bring out a lot of real world applicability. As you can see here in the flags, maybe we want to compare the United States with Canada in some regard. Ultimately, what we're going to be doing in class is doing a confidence interval for two proportions, as well as a hypothesis test for two proportions. And if you remember, when we do that confidence interval, before we had that p hat plus or minus z star square root of p hat 1 minus p hat over n. Instead of that, which is for one proportion, if you look at the bottom here, the standard error for p hat 1 minus p hat 2 is exactly what we have here. So essentially, we're doing the p hat 1 minus p hat over n for each parameter, and then we're adding them together, then taking the square root. So it's very similar to the formula that we saw before, and I'm actually going to show you in class how to do this in your calculator, so you rely a little bit less on memorizing formulas. There is some good news when it comes to assumptions and conditions for two proportion tests and intervals. The conditions that we checked before for a one proportion confidence interval or test are exactly the same as what we're going to see now, with one addition. So first off, we have to have a random sample within each population. Our sample size from each population also has to be less than 10% of the population size. And then we still have that NP, N times 1 minus P, or N times Q. Each of those have to be greater than 10 in each of our samples. Now, the additional condition that we have is that between the two groups, so if we're talking about the United States in one population, Canada in the other population, the additional condition is that we have to ensure that they are independent from one another. So they cannot be from the same sample or population of interest. One sample has to be independent of the other. And just a quick note here, we have to check these conditions for each of our samples, okay? So you have to ensure that both samples are random. You have to ensure the 10% condition for each sample, and so on. So very similar to what we've seen before, just a little bit more writing when it comes to checking the assumptions. Just like before, if the conditions are met, or if all the assumptions are met, instead of the name being a one proportion z interval for our confidence interval, it is now going to be a two proportion z interval, which kind of falls in line with what we've seen in the past, but now we have two proportions. So when the conditions are met, we are ready to find the confidence interval for the difference of two proportions. So when I say the difference, that's how we want to interpret what the interval is. We would say, like, we are 95% confident that the true difference in proportions is between this number and this number. So if you look here, our top equation, before we had p hat plus or minus z star, yada yada. What we have now is p hat 1 minus p hat 2. So again, we're talking about the difference. So subtract your two sample proportions, p hat 1 and p hat 2. We still have plus or minus z star. Z star is exactly the same as before. And then we do have that new standard error. So times the standard error of p hat 1 minus p hat 2. And exactly what we have down here is what we're going to fill in for a standard error here. So instead of just square root of p hat 1 minus p hat over n, we have to include both p hat 1 and p hat 2, and then add them together, take the square root. So main thing to emphasize here is that when we interpret a confidence interval for two proportions, we again are only referring to the difference in proportions. So we are 95% confident that the true difference in the proportions is between this percentage and this percentage. The last thing I have to talk about is a two proportion z-test instead of the interval. We still have that idea of a hypothesis test for two proportions. So just like before, we want to start by defining our parameters. Here we're going to have P1 equals the true proportion of, and then you insert the context. And same thing with P2, define that other parameter as well. But in our null hypothesis, we almost always want to assume that P1 is equal to P2. So we're going to assume from the beginning that there's no difference in P1 and P2. And our alternative hypothesis then is that either we want to know if P1 is greater than P2, if P1 is less than P2, or simply P1 is not equal to P2. This, of course, will come from the context of the problem. Sometimes I will say, is there evidence that the rate of graduation in Canada is higher than that of the United States? So just be aware of how you define P1 and P2, and then adjust your inequality symbol accordingly. Just like before, once we go through, check our assumptions, name the test, all that stuff, the test statistic, the z-value, is exactly the same as before. So that doesn't really mean a whole lot to us, but we do have to record that on our sheet. And then in phantoms, that was the t, the z equals some number. Obtaining a p-value, the O in phantoms, that still refers to obtaining a p-value. And that protocol of rejecting or failing to reject is the exact same as before. So if that p-value is less than our alpha, if the p-value is low, reject the null. Whereas if it is greater than alpha, you're going to fail to reject the null. So just know that there's nothing new there. Your conclusions should still be stated in terms of the alternative hypothesis, and you can either reject or fail to reject the null. Last thing I'm going to point out is that on your calculator, it will ask you for a two proportion z-test if you want to pool your data. I'm not going to talk too much about what that means. All you need to know is that you're never going to pool your data. We never deal with a situation in our class where we have to pool it. So just know that on your calculator, you will always hit no for pooling your data.